energy that we use in a circuit comes from the EMF of the battery, and it goes through a series of energy transformations. It starts as chemical energy inside the battery. The chemical energy is converted into electrical energy, which is going to be potential energy from the charges separated between the positive end of the battery and the negative end. That potential energy is converted into kinetic energy as the electrons travel along the wire, and then that changes into thermal energy. Power is the change in energy per unit time. The definition we use for power on the AP Physics 2 equation sheet is P equals I delta V. So the power of a battery is the rate of the energy transfer, which is the change in energy over the change in time. And if you remember, the change in electric energy is equal to Q times V. Q times V can also be written as delta Q over E, because EMF is the potential, the change in potential, and that Q over T is the same as current. So from this, we get to the power of a circuit equals the current times the change in potential. IE, or I delta V, has the units of joules per second, but we can also use the units of power that we used back in Newtonian physics, which is the watt. And a watt is equal to a joule per second. So let's do an example. How much current is drawn by a 75-watt light bulb connected to a 120-volt outlet? This is something we could have in our house. The 120-volt outlet is our change in potential. The 75 watts is our power. So we're going to figure out how much current that takes. We're just going to plug our values in, and we get a current of 0.63 amps. This is a reasonable answer. Currents in a light bulb are going to usually have a magnitude of 1 amp, or somewhere around 1 amp for a light bulb or other household items. So 0.63 amps is the current that the light bulb would draw. All right, that's pretty much the summary of power. Now I want to talk about circuit diagrams. So when we look at circuits, we can draw them as pictures, but that's a lot of work. And in engineering, we can get complicated circuits. We don't want to have to draw these pictures, so we're going to use a circuit diagram. So you can take this circuit, and you can draw it like this. So what are all these pieces mean? Well, a battery in a circuit diagram is drawn with 4 lines, horizontal lines, and you'll notice that there's longer lines on the top of this and shorter lines on the bottom. The longer line signifies the positive end of the battery, and the shorter line at the bottom signifies the negative end of the battery. Anytime there's a wire, we just draw a line. Anytime we have a resistor, we do an up and down shape like this. A light bulb is drawn as a circle with a little loop in the middle. If the wire splits, at any point the wire splits into 2 different parts. It's called a junction, and that's just going to be the 2 lines, and then it splits into another line. If we have a capacitor on our circuit, it's drawn with 2 parallel lines. And a switch or a break in the circuit, a place where we could break the circuit, is drawn like this. So for the following circuit, we have a battery, we have 2 capacitors, and we have a resistor. What is the circuit diagram that best represents the above circuit? Well, notice from the battery we have a split that goes to 2 capacitors. So we're looking for a circuit that starts with a battery and then splits to 2 capacitors. This circuit has a battery, but it splits to a resistor and a capacitor, so that's not right. This circuit doesn't have a split or a junction, so this is not right. Here we have a battery. The positive end is going to split into 2 capacitors. Then they join back together and go through a resistor, which is the same as the picture. So A is the correct answer. So there are a couple of laws about what goes on in a circuit, and Kirchoff's junction law is the first. These are called Kirchoff's laws. The junction law says that the total amount of current is not going to increase or decrease, but the total amount that goes into a junction is going to equal the total amount that goes out. That means if I1 is what goes into the junction, then what comes out is going to be I3 and I2, and I2 and I3 added together equal I1. This basically says current is conserved. It's not lost or gained. It just divides into two different sections. So another way we write Kirchoff's junction law is the sum of all the currents that go in equals the sum of all the current that comes out. So here's an example. We have part of a circuit where we have a current going across a resistor of 2.5 amps. And that is split into two sections. One has a current of 1.5 amps, and another, we don't know the current, but we know it goes through a 200 ohm resistor. So what is the current in the 200 ohm resistor? Well, we're going to use Kirchoff's junction law. The current that comes in, which is 2.5 amps, equals the current that comes out, which is 1.5 plus something. So 2.5 minus 1.5 is going to give us a current of 1 amp. The second Kirchoff law is Kirchoff's loop law. Kirchoff's loop law says that the change in potential through a loop is going to be 0. That means if you add all the change in potentials at each point in the loop, it's going to come to 0. So the change in potential across the battery, plus the change in potential over the wire, plus the change in potential over the resistor, plus the change in potential over the resistor, all added together, it's going to equal 0. And we can see that graphically by looking at how the voltage or potential changes as we go through the circuit. We start at the negative end of the battery. There's no potential at the negative end. At the negative part of a battery, your potential is 0. So that's the first part of our graph. We have 0 potential. Then we go through the battery. As we go through the battery, our potential increases. It goes up to the maximum potential, which is at the positive end of the battery. Then we're going to travel along the wire. When we travel along the wire, in an ideal case, there's no resistance, so our potential is constant. Then we get to a resistor. Our first resistor, so we're going to go through the wire to the first resistor. Our first resistor will lower the potential a little bit. So that's our change in potential from the first resistor. Then we go through a wire again, so our potential is constant. Then we go through a second resistor, and our potential decreases again. So now we're at the end. We're going to travel through the wire, no change in potential, and we get to the beginning of the battery where our potential goes to 0. So the sum of all the changes together is equal to 0. So for our last problem, we're going to try to figure out what is the potential difference across the 200 ohm resistor. These problems are a little bit more complicated, so I'm going to do step-by-step solution to it. So our diagram shows a circuit. It has two batteries, a 4.5 volt battery and a 3 volt battery. It has three resistors, 3 volts, one with a 3 volt drop, one with an unknown drop, and one with a 2.5 volt drop. We know that if we go through the entire loop, our total potential will be 0. So here's how we're going to solve this problem. First, we draw a circuit diagram. Well, it's been drawn for us. Now we're going to decide the direction of the current, and we draw current with arrows. Now, even though the current actually comes from the movement of electrons, we traditionally choose the direction to match how positive charges would move, which is away from positive charges and towards negative charges. So even though the electrons really move in this direction, towards the positive, we're going to draw our current the opposite way. So we always draw from a battery away from the positive is the direction of our current. This is the positive end of the battery, the negative end. So we're going to draw our current this direction. And we continue it throughout the entire circuit. We've drawn our direction of our current. We have our circuit diagram. Now we're going to travel around the loop using special rules for positive and negative to find the sum of the potential. So we're going to start before the first battery. And here are our rules. As we go across a battery, from a negative to a positive, our potential will increase. If we go from a battery from a positive to a negative, let's say this battery direction was switched. We would count that as a negative potential. But in this case, we are still going from negative to positive, so it would be positive. But as we go over a resistor, our potential will decrease, so that'll be negative. So we're going to find the sum of all the potentials of our loop. So we're going to apply our loop law. So the sum of all our potentials is going to be equal to 0. So let's do our first one. Our first one is 4.5. We're going from negative to positive, so it's a positive 4.5. Now we're crossing another battery from the negative to the positive, so we're adding another 3.0 volts. Now we're going across a resistor, so we have a negative 3 volts. So 4.5 plus 3.0 minus a 3.0 volts. Then we're going to go across another resistor. We don't know the potential there, but we're going to write it as potential across the 200 ohm resistor. It's negative because it's a resistor. And finally, we cross our last resistor. Since it's a resistor, our potential goes down, so it's negative 2.5 volts. Now we're going to solve this equation. We sum all our potentials together. We leave our variable, and we're going to solve for the potential across the 200 ohm resistor. And the answer is that potential is equal to 2 volts. So the answer is A.